For joining this Advanced Valve Solutions webinar. We are running a series of webinars where we take a look at the steam and water control valves manufactured by Hora in Germany and at our isolation valves manufactured again in Germany by the company PERSTA and the applications that these valves are used for on power stations. Today we discuss some of the isolation valves made by PERSTA. In other webinars, we take a look at subjects such as bypass valves, feed water control valves, dual shifting demands and challenges, effective isolation, and so on. If you'd like to attend any or all of these, you'll be given details after this webinar. Today, our webinar lasts for around an hour with an excellent short video halfway through, giving an opportunity for a comfort break or a coffee top-up for those lucky enough. We welcome any questions that you may have, and hopefully you'll see on the right hand side of your screen a chat function. Please enter any questions there, and the more the merrier. We hope to be able to answer as many as we can by the end of the session. Those that remain unanswered, we will get back to you afterwards shortly. Karel van Wijk is in our new studio in the Netherlands, and I know that he is keen to get away, so I'll hand you over to the Netherlands now. Karel.
Good morning, everybody. I'm really happy to be back, and I'm really happy to have the opportunity to tell you something more, or quite a lot more, about our factory PERSTA in Germany. PERSTA making the complete line of gate lobe check valves and stop check valves for water and steam applications. As we know, everybody likes to have German machined materials, and PERSTA is at this very moment really leading in the market of development of new valve lines which are needed for the new requirements on HVAC power stations, specifically on the very high ramping up figures we need nowadays. Before we do that, we'll have a look into a few topics. The topic of the drain valves, there it is again. The topic of materials and what is the difference between castings and forgings. I'll not spend too much time on that, but I really want to share this information with yourselves. We'll talk about the new developments in valve manufacturing, how we're going to deal with very thin walled valves and how can we make these valves very competitive, and then we'll have a look in our marvelous line of stop check valves, which can be of high interest for everybody who is really busy with ESME approved boilers. Okay, what can we do? First of all, what is the program of PERSTA? As mentioned, we are making gate lobe and check valves. Gate lobe and check valves, a standard line gate lobe and check valves which is used for centuries in the power market, but also in the chemical, in the petrochemical industries, where we do have the need for steam which is used for heating purposes, steam which is used for, well, whatever application. We have a complete standard line, so the standard basically to DIN, and we are manufacturing a complete line of high-end gate lobe and check valves for steam applications. And then you really have to realize that we can take valves for coal-fired stations, valves for HVAC units, all kind of high-demand valves. Okay, we go to casting and forgings. Why is that so extremely important, and why is it becoming more and more important? I think that is a necessity which we really have to explain shortly. Many valves, and certainly when you look in the ESME environment, are based on castings. WC6, WC9, C12A, it's all casted material. And how is casted material, how are cast bodies of valves created? Well, cast bodies of valves are basically created by making the base material for the valve body liquid, so heat it up till it is liquid, and then pour this material into a form, and that form is normally hidden in a sand cast. So this is basically the casting, this is the core, this is the inside of the valve, and then I have also a complete form which I will realize. Casting, the forming valve bodies, forming all kinds of products based on castings is done for a very, very long time. And when we started in the early days with cast iron, noddy cast iron or cast steel, the material was very, very, very liquid. So it is like pouring a cup of tea. That liquid material will go into the hole in the mold and will fill the complete gap. The problem is that when material gets solid, it will shrink. And you need in the material enough liquid material left which can, let's say, compensate the shrinkage of the model you want to achieve. And that is the knowledge which is based in the foundry. Well, in the UK you have many, many foundries, so that knowledge has been gathered over the last 200-300 years. That is not an issue. The problem is that when we take high alloy materials, and due to the need in the new power stations, we are going from 420 to 450 to 600 degrees C, other high alloys have to be created. But the problem of a high alloy is that that is not as liquid anymore as the normal cast iron was in the old days. So that high alloy material, you can see it as a kind of a syrup, very slow moving, and when that material solidifies, it is very, very complicated to compensate the shrinkage. Well, to do that, we have, for example, a riser. This is called an open riser. That if this material is still solid, you can see this is bigger, so this is a longer liquid than the material which solidifies here, and then the shrinkage is compensated. Another drawing, you can see again the model, you have to pour in, you have risers, that is all to compensate the shrinkage. Complicated process, but that process is always based on gravity. So the maximum force you can apply on that material is just gravity, and that is not much. If we see a nice casting, the casting looks on the outside really smart, really good, no discussion. But if I look on the inside, and we talk here about a very low pressure steel valve, so nothing special, you can already see that I do have got here and here and here and in the flange really casting defects, shrinkage holes. Well, the design of a casting is always done based on the fact that you will have shrinkage holes, that you will have material defect, so the valve itself will be strong enough. But you can imagine that if I apply enormous forces on this valve body, or when the shrinkage hole is also connected with cracks, with gas inclusions and all other mistakes in a material forming, that is a non-solid material, it is a not a good material at all, and certainly when I have to heat up and cool down these valves very, very quickly, it can lead easily to defects. Not the way forward. What is the way forward? That is forgings. There are a lot of methods to forge material. In the intermediate film we will see the forging going on, and the forces applied by forging are going up to 200 ton meter. That does mean that we have a block of 200 tons which falls down 1 meter. That kinetic energy is used to form the material into basically its mold. That is it. I take a block of very hot material and I forge that material into the form I want to achieve. And you can imagine that that material does not have any material defects anymore. It is rigid, it is solid, and with that form technology you can make materials much thinner. And thinner materials are better for heating up and cooling down. That's obvious. This is one of the presses and one of the hammers you have. You have the upper beer and the lower beer. These two huge, massive pieces of steel are coming together, and in between is the negative mold where you forge the very hot material in. And it is something we'll see live when we have Vels and More really at PERSTA. You can really feel it, you feel the floor shaking, you smell it, it's really marvelous. The fire is done they have sawdust which they throw on the product. That is when the sawdust is in the mold. When the mold comes down, it's burning and it gives gas pressure, so that's the model is released from the dies again. So that is necessary. Another feature of this material, of this way of forming your models, is that you can play with the grain structure. If you can see it in this way, you can now, let's say, stretch the crystal structure of the material, so you can really make the material much stronger in the direction I want to have it. That's another feature. So it is not only a solid, rigid material without defects, but it is as well with stretched crystalline structures, so that you can really apply more force in a certain direction. This is the old way. It is not that clear, but if we take this picture, we'll see the development where we're in at this very moment. In the old days, in the old coal-fired days, we had P22, 2¼ grow material as the maximum material. Later on, we developed X20, 12 grow moly. X20 has been for a long time the maximum material in coal-fired stations, certainly in the UK. But relatively soon, we have developed P91. P91 is a double grain structured material. It is very, very strong and is capable of taking higher pressures and higher temperatures. But it is not the end of the story. The new, most HRSG units nowadays are equipped with P91 main steam lines, P91 superheaters. So that is the, let's say at this very moment, the base material. But there are better materials. P22, 12A, C12A, a cast version. It can be thinner. But the future is in this corner. The future is in P92. And you can see, if I have a wall thickness of 45 mm in P91, I have only 34, so a 20% less wall thickness. But 20% less wall thickness means that if something has to heat up very quickly, it is hotter sooner. So you can apply very high heat rates to that material. And the next generation, that is P92 MOT material, that is the next generation, that is probably another 20% thinner. So that's another 20% faster in heating up. And if the requirements are there, but that's something we'll address a little later. Our standard valve. This is the material part. I really would like to say something about drain valves. And then we go to the new developments in this very thin material applications. Drain valves, we told you something about it in the HORA presentation as well. Drain valves are of very important pieces of kit nowadays in power stations. If you have to start and stop quite a lot, the drain valve is one of the weak spots of the installation. And why is that? Drain valves are there to release condensate, therefore it's a drain valve. And in that condensate is a certain number of energy in that water. And if I bring the pressure down to environmental pressures, that water droplet, that 1 liter of water cannot hold all the energy anymore. So a part of the energy is transferred into steam, and what comes out of a drain valve is a steam-water mixture. That flashing process basically is harmless. It is like opening a bottle of sparkling water. You see that bubbles comes out and you get a water steam mixture. But the problem is that the water steam mixture has a much higher volume. So that 1 liter water where you start with is now transferred in, let's say, 300 liter, including 55% of water droplets. And when that is done in a 1 inch on 1 inch valve, my entrance velocity is a meter, my outgoing velocity is 300 meters. And you can imagine that if I have water droplets of 300 meters a second, that is eroding away everything. And honestly, we have a whole collection of nice pictures of all kind of damaged drain valves. You can see you really get enormous holes in the material, and that is not the best way forward. Why? Because then you have a leaking valve, you cannot maintain pressure in your boiler, and that is one of the features what we can achieve if we can close the boiler, if we can lay up the boiler overnight when it don't have to run. We can then close it, and with that, when the boiler is closed, you can maintain the pressure and you can make a hot start of a warm start in the morning instead of a cold start. The solution, as discussed already, I take this picture, we'll have to split the functionality in the valve, basically the sealing edge and the control edge, two different things. When you open the valve first, you avoid significant flow through the valve till the valve is completely open, then you get really good flashing. This part of the valve will have wear and tear, but the moment I'm trying to close the valve again, I first of all stop the flow going through. Here are the sealing areas, they're still far away, so they are not in danger, they are not damaged by the flow, because the flow here is just water. It comes down, and then I have a touch down and I have a sealing drain valve. And to transfer that into a valve, we have designed with PERSTA, or PERSTA have designed this valve, and that is based on a small entrance, an extended outlet, so let's say an inch inlet, 3-inch outlet. That does mean that by the 3-inch I reduce the outgoing velocity extremely. Further on, it is an angle type valve, very important, because an angle type means that my water steam mixture don't have to make any bends or curves in the valve body anymore, so that the erosion, which we normally find in these valves, is not occurring in these type of valves. But even these valves will show some wear and tear, so it is extremely necessary to make the trim of this valve changeable. Very quickly changeable. So we have the bonnet, you unbolt the bonnet, you pull out the spindle, the seat here is just clamped in, so you lift the seat, you replace the seat, and you have basically a new valve. Wear and tear on the valve body in that way is avoided. Please take care that you use original packing materials, otherwise the clamping process can't be correct. Bring all the valves in a header like this, and you have a drain system which is fit for purpose and will do its utmost. The utmost performance, and 400, 500, 600 starts later, the valves are still tight. Experience still now. This is the valve in practice. You can see I have a small inlet, a big outlet, and this valve is based on a very fine forging, and that forging we've seen how that is made. Block valves in the line itself are these kind of valves, and what we use is we have Belleville washers in this valve installed. It's a bonnetless type valve. The spindle, if you close the valve, you bring the Belleville washer, the cup spring on tension. If there is any shrinkage or grow of the spindle, that will be compensated by this Belleville washer. But that is the on-off valve which belongs in the system. You cannot reduce serious pressure over these kind of valves. A new development before we go to the break. These are a few pictures of our more special valves. So these are really the main boiler steam stop valves and so on and so on. But also in this field is a certain development. And one of the developments PERSTA has made is the electrobeam welding. Electrobeam welding is basically welding with a laser beam, with an electro beam, and that does mean that you do not have to bring in additional material to weld bits and pieces together, but that you melt bits and pieces together. So you just make a very thin melt, and these two halves of the material will melt together. The huge advantage of this procedure is that you can see it happening here. This is basically the material, and we are building valves in F12 and F22 for a very long time. The new development is that this procedure is now also approved for the P91 material. Ultimate effect is I now have, let's say, half a valve, so I can easily approach my seat area. So I can make now a valve as an integral seat. I don't need a special seat retainer anymore. And I can now melt the valves together. I have a rigid valve, and if I play around with my forging process, which we have in-house, so that is very easy, we can really make a forged gate valve which can apply the highest ramping up figures in the future. This is again the procedure. These are the half scales. I don't know whether you can see it. Marijn, can you put it? Yeah. These are the half scales, and you can see if it's machined. Welding is done under vacuum, so we need a huge vacuum chamber, but once we can make very, very good valves. This is the grain structure after I have done. You can see. I doubt whether you can see it on the presentation, but here you can see a little bit the weld or the melt, and this is how the melt looks like after recrystallization. If that is, then you have just one material. You cannot identify that this material was two pieces. It is just one rigid material. So you can also apply a factor 1 on the weld, of factor 1 basically on the melt, because it is not a weld but a melt. Okay, before we go to the break, before we'll go more interested into main steam stop valves and in the main steam valves, Martin, do we have got any questions in so far?
Yes, we've got a question. Does the electron beam welding process introduce any heat affected zone or area? And if so, how is this dealt with? So the electron beam welding, does it introduce any heat affected zones?
It does, absolutely. Very good question, by the way. Yes, of course, you make a melt, so you will have a heat affected zone. First of all, the heat affected zone is very thin, because the heat impact, the heat brought in is limited, so the heat affected zone is limited. But after the valve is melted together, the electrobeam welding has taken place, the whole valve is put into an oven to normalize the whole situation, and in case of a P91 it is heated up to 1100-1200 degrees or something like that to be to have a recrystallization. What a word. This recrystalline process makes that you cannot identify the weld afterwards, so it is just one integral piece of metal. You have to heat treat it just like you have to heat treat other welds as well. Welds where you have to add material, you have to have a heat treatment afterwards. If someone wants to go deeper into this issue, I would really be happy to have a separate meeting to go really in depth in this process.
Okay, I don't know whether the camera's on me or in the studio. If it's on me, that's a good answer. Thank you very much, Carol. That was clear. Thank you. That's the end of part 1. I hope you all enjoyed it as much as I did. We're now going to have a short video for the coffee and comfort break, and see you shortly for the second part. If you can. Hello, welcome back to the second part. It's a very impressive video from PERSTA of their production facility, which I hope you enjoyed. For those of you who hasn't seen the factory in person, as Carol says, hopefully you get to see it before too long. We're going to carry on with the second part now. May I remind you that any questions that you have, use the chat box on the right-hand side. And yeah, as always, the more the merrier. So back to the Netherlands and over to you, Carol.
Martin, thanks again. Welcome back. I hope you enjoyed the film. What we saw in the film maybe was this hammering things with these yellow hot pieces in the middle. That is the way to process, to make the die, to forge the model in the die, and with that procedure we can just make this failure-free material. Okay, let's talk about gate valves. If we go back in the history of the gate valve, the old Mr. Weir and the old Mr. Durrance developed in 150, 200 years ago, the parallel slide gate valve. Why a parallel slide gate valve? Because in that time they were capable of making plain parallel seats, so you can really make a gate valve. That gate valve is based on two plates which are moved parallel, guided by the seat up and down. And guiding by the seat up and down does mean that the seat also is basically scratched by the discs, by the plates, and together with a whole spring section in the middle, it is not an ideal valve. It is a valve as long as you never use it, it's a nice valve. But if you have to operate this valve once, twice or 3 times a day, that valve will die on wear and tear fairly quickly. What the development on the continent was, is that we have developed valves which are applied in higher pressures and higher temperatures. The coal-fired stations in the UK stop at 185 bar, 540, 560 degrees C. Our European supercritical coal-fired stations are going up to 330 bar, roughly 650 degrees C. And in these applications, parallel slide gate valves are not functioning properly anymore. And in this respect, we had to make a development step, and the European development went to what we have called the tapered parallel slide gate valve. A tapered parallel slide gate valve does not mean that it is a wedge valve. It is not. It is a tapered parallel slide gate valve which, used as a parallel slide valve, has a huge feature. And that feature is, you can see that in the middle of this picture, is that as soon as these two discs, so it is not a parallel position anymore, but it is a tapered thing. This, as soon as the discs are lifted off the seat, the guidance of the two discs is taken over by a separate rail. A separate rail with a low friction, because the surface of that rail is much bigger, so you have a very low surface pressure on these rails, and the guidance is then done in a very proper way. And the valve is not damaging its seats more. And just before the valve is completely closed, the disc is touching the seat. That's a huge feature. It's really a huge advantage. How do we make the valve body? What we saw, that valve body is pressed as well. It is forged. It is a forged valve body. And you can see, as soon as I press this hot piece of metal in a model, I can press the valve body. In this animation you can see it as well. This animation is showing as well the grain structure, and you can see that the flange neck, the neck between the inlet, the stub ends of the valve and the valve body is now forged into a certain direction, in a certain line, so that we have a much better strength in the valve forging process. What comes out are these kind of valve bodies, and you can already see in this raw material valve body that you have a rail integrated, and that rail takes care that the guidance of the discs is done properly. Well, you can imagine pressing a body like this does not take that much time, but to press it, to set up the presses and to heat up the molds where it have to be pressed in takes a lot of time. So ultimately we can make this happening when we press a lot of valve bodies in one go. Advantage is that we do have a big stock of these valve bodies, so we can supply you very quickly with a main steam stop valve or whatever. So if you have a sea inspection, we could, if we want, build a valve in the sea inspection time. So in 30, 40, 50 days it is possible. Advanced, we appreciate to have a little bit longer, but if strictly necessary we can do it. And you can see this is a little of our stock of valves what we have, and that is valve material F22, P91 up to 14 inches all laying around. So this is really a very impressive stock. I mentioned already 14 inch. 14 inch is the maximum size we can use for these press bodies. Otherwise there is no press in the world anymore who can press it. So if you going bigger, if you have bigger valves, you get the so-called block valves. And these block valves are built as valves for free-formed really big blocks, and you start machining. You machine 2/3 of the block away, and the end result is this valve. You weld on the stubs, you weld on the neck, and you have an integrated system of seat retainers. Very good valves, developed for coal stations, quite often used in HRSG units, but these valves do have limitations. If I have a look, this is the valve after heat treatment. You should clean it and it looks smarter. But it is the big block with welded on stubs. But the wall thicknesses of this valve are not always the same. So this valve cannot be heated up very, very quickly. And in the new requirements of the new generation gas turbine H3G units, and our friends at Siemens are taking the lead at this very moment, they are needing valves which can ramp up with 30, 40, and the requirement in the future will be roughly 50 degrees C per minute. Can you imagine? 50 degrees C per minute. That is absolutely ridiculous. So now we have to have a look what kind of developments can we make, how can we build valves which can last for the lifetime of the boiler, because I'm not interested in changing my main steam stop valve every year or every 2 years. What kind of developments can we have? And then we come back to this picture, we have seen it. We were, what we say, at P91 as the standard material for the valve, but we go further. We have P92, and these are the NF12, are the chrome nickel based materials. That is a valve which you should afford yourself. That is a material which is extremely expensive and is only basically used for temperature applications above 700 degrees C. So that is at this very moment technical feasible, but too expensive. The material in between will be P92 MOT. Most probably that material will be called P93. P93 is the material that is thin enough and strong enough to build valves which can last in this high temperature ramping up situation. If I see the old valve, the old style valve, and you can see we have already tried to shape the valve body as round as possible to reduce too much wall thickness differentials in the valve, and we can now assume that this should be a valve which can do it. When these first valves are built, we could not calculate exactly the material stress, so we could not calculate what was wrong. Afterwards we have built the calculation, we have developed the calculation methods to build these valves, and on that point we can see that we have a lot of color differentials. Color differentials mean stress. Color differentials mean material stress, and material stress is something I want to avoid in my valves. Whether I like it or not, I have to get rid of that. In the old days we had the seat retainer. The seat retainer is necessary to bring in the valve, because you cannot other way weld, that has to be welded in the valve after the valve is constructed, but the seat retainer itself is also representing certain points which you cannot check afterwards. You cannot do a dye penetrant behind the seat, so then you have to machine the seat out, and that can only be done when you dismantle the complete valve, and that's something you want to avoid. So the new generation valves is made with an integral seat, is made out of another material, and these valves are machined out of one huge block. 8 days, 8 nights, a boring machine operator sitting and looking at what the machine is doing, and then at the end I have the valve body. I have a valve body which does have an optimum shape on the inside, on the outside, but does have the right roughnesses over all the, throughout the valve, and a valve with an integral seated construction. So let's say all the heat which is now brought in the valve is distributed very, very equally on a body which is as thin as possible. That valve, if designed correctly, can withstand, of course, the static pressure and temperature, no doubt about, otherwise the valve would not be allowed to go in, but is also capable of ramping up and cooling down extremely quickly. And the next generation of these valves will go for even higher qualified materials, which are even harder to machine and which are also fairly complicated to weld. But in all respect, PERSTA does have the capability of end forging and welding, so they are really extremely competent, and they are at this very moment leading in the market for these fast ramp up and cool down valves. this is also a very nice development. This is a valve which we are using for the hot reheat gate valve. Hot reheat gate valves, and now I really have to tell you a detail about these valves that are the really complicated valves. If I do have a casting, then the cast body is a really fat body. Normally it's a little bit reduced bore. Then I get a welded in seat retainer, like this. Here's the seat retainer welded, so I do not have that much, let's say, contact between the seat retainer and the valve body. And on the seat retainer I need a stellite seating. Okay, what is happening when this big valve, because these valves are 5,5 tons of casting in C12A, that's a really interesting lump of material, believe me. So it takes time to heat that up. What is the effect when I now bring in, I'm now starting my installation, and very soon I'm entering 600 degrees C steam, or 580 or whatever. You can imagine that the body is still cold. If the body is cold, there will have to be an enormous heat flux through the body, into the body. Before the body is heated up, it will take time. But if you start your boiler, if you start your hot reheat, you don't have that time. So what is the ultimate effect? Your seat will heat up very, very quickly. That is hanging free in the 600 degrees C steam. The backyard is still cold, is much colder. Well, if there is something stellite don't like, is it flexibility. Stellite hates it. So what's the ultimate effect? The stellite is breaking off my seat retainer, and my stellite is deformed into half bananas, which are found on the bottom of the valve. But believe me, you can make an emergency stop because this valve failed completely. How do we solve it? And you can imagine that if I do have an integral seat, if I have this material completed and my valve is like this, I now take a big layer of a buffer material, a butter layer of, let's say, Inconel or something like that, and on that buffer layer I now place my stellite. Well, that butter layer, this red layer, is flexible, so that red layer can absorb the differences in expansion of the different materials, but at the same moment the complete heat flux can go into the valve body instead of just through this weld. So there is much more heat going in combination with a valve body which is, due to the material, much thinner. So this design valve can ramp up with 30 degrees C. This design valve is basically 2 to 3 degrees C per minute. Well, that is a fundamental differential. Consequently, these valves don't fail, these valves will fail. This is the construction of basically a high ramping up main steam stop valve, but it is also the construction we use in the hot reheat valve, because the hot reheat valve does have exactly the same problems. On the picture left you can see pressed half scales, where I take in the old days a C12A casting of 5 tons and a lot of repair welds to compensate the casting failures in that casting. I now take a 2.5 inch thick piece of 91 plated material and I weld this body together. And I have 2 of these half scales. It is a little bit imagination necessary, but nevertheless I end up with this valve. This valve with a pressure seal does have a weight of, let's say, 1.5 ton versus a casted valve of 5.5 tons. And the wall thickness of this valve is basically roughly the same as the wall thickness of your pipe wall, of the hot reheat pipe. So basically this valve can ramp up and can cool down extremely quickly as well. We have a huge welding machine, and that huge welding machine makes it possible to weld continuously the big valves. Continuous welding means that you don't have to start and stop your welding procedure. You can keep the temperature much better under control, and you can get an absolute marvelous welding quality. And that is important. But this machine opens as well the possibility to give you additional service. If you have to replace your main steam and your main steam stop valve, for example, your downtime is critical. If you remove your bits and pieces on the boiler deck, you want to replace that as quick as possible. Well, this big welding machine makes it possible to make these kind of assemblies, to make an incoming piece, 2 valves, an outgoing piece, all the balancing valve stuff around it. And that means that I have basically only 2 welds to make on the boiler deck. They are so far away that 2 teams can do that. So in a very short downtime you can replace your main set on your main steam line. It is a feature. It is not something you should do as valve manufacturer, but I think it is more a service piece of kit that we can supply you with these kind of things. And believe me, quite a lot of people are really happy about it, and the downtime of your installation is minimized, and the quality of all the valves is of the highest level, because that could be done under ideal circumstances. Another funny valve is, another valve is, for example, this one. This was a request also from an UK power station, a very odd valve, a 3-inch inlet, an 8-inch outlet. Yeah, that was the pipe structure where it should be placed in. There is a material, it started with F12, it ends with P91, but that was also defined by the pipe it should be placed in. Well, the question was, can we build that? Yes, of course we can, and we supplied this valve in 12 weeks' time. So it was a nice, really nice piece of kit. Okay, I'm going to my last subject, and that is called stop check valves. Every SME boiler where there are 2 on site needs a stop check valve. That is a requirement, and that stop check valve is basically a headache. Because what is the issue? This should be the normal situation, a check valve and a gate valve. Whether that's a parallel slide or a taper parallel slide is not that interesting. But now we have redesigned it into a stop check valve. It's only 1 pressure containing part instead of 2 pressure containing parts, and of course we can weld the whole show together, so that makes it easier, but still 1 pressure containing part is better than 2. The normal way forward is a Y-type stop check valve, a Y-type globe valve, a Y-type globe which does have a stop check function. And the Y-type globe valve is based on a globe. This is the disc, there is a guidance, and the spindle is not fixed, connected with the piston, with the plug, and that piston have to be lifted. But the weight of that piston is enormous, so that is not that simple. We can see that the required forces for these stop check valves, for these Y-type globe valves, are enormous, and that does mean that your steam, which is in your system, really have to push the plug upwards instead of that the swing type function is the case. If we make a comparison, this disc will have a weight of roughly 30 kilos, and the same valve as stop check valve, the piston does have a weight of 300 kilos, so 10 times more. Well, you can imagine that you need much more pressure to open that. And furthermore, the flow characteristics through that valve is shit. So that flow has to go up, then it has to come down, and it has to make another bend. So the K factor of this flow is worth compared with what we have as the stop check valve. I just have the valve to be moving. And what we can see is the disc. This is a free moving disc. So the green component in this animation is a free moving check valve. And if I close that check valve, the white part on the spindle, this part, will then block basically the disc of the stop check valve. And consequently, that valve is tight and can be seen as a taper parallel slide gate valve. When you open the closing disc, let's say the blue disc on the right side, when that is in open position, it is just a swing check valve. It's a very good system, and if we have calculated, we can find that we have a much better flow pattern through the valve, and we have a much better characteristic of the valve. We have here two simulations. The left simulation is the flow through the valve as a stop check valve based on a Y-type globe valve, and you can see the flow will have to move up and downwards. So the characteristic of that valve is poor compared with the normal swing check valve, which is an animation on the right side. That's the PERSTA design, and you can see the flow can just go straight on. Consequently, we have seen that the pressure drop in the Y-type globe valve version of the stop check valve is much higher than the pressure drop we have in the normal stop check valve as we build it. Consequently, you have more pressure on your turbine, so you have more power output. So that is really cash money. Another thing is that the swing in the swing part of the check valve does not need a lot of force to open. So if you have the piston of the globe that have to be pushed upwards, well, that is not a smooth process. So you have also, in this case, pressure waves in your primary steam pressure, which your steam turbine don't like either. If we calculate that, we have here, for example, a main steam stop valve calculated. On the left side we see that the pressure drop of this valve is 2.6 bar of the Y-type stop check valve, and our valve, the PERSTA stop check valve, does only have 0.55 bar pressure drop. So I'm basically earning 2 bar pressure. Or if I calculate it otherwise, I have a loss of 0.55 megawatt. In this case, I have a loss of 1/10 of a megawatt. Well, that is roughly half a megawatt more income. And that is really cash money. Another calculation we made is we have, in this case, a 24-inch hot reheat. Pressure drop is again 0.35 bar of 0.1 bar. So it's also a quarter of a bar less loss. Good valves available if you like it. And that brings me basically to the end of this PERSTA overview presentation, this way of how can we do it and how we see the development in the new world of valves. Are there any questions, Martin? I cannot imagine that there are no questions.
Yeah, a couple that have come through, Carol. Firstly, using the electron beam welding procedure, is there no longer a need to have special seat preparation, i.e. stellite coating?
Say it again.
Using the electron beam welding procedure, is there no longer a need to have a special seat preparation? So it's separating the electron beam welding of the body versus the seat. Does it introduce any additional layers or coatings at all?
It does not, because the two half scales, if you can see this thing, if you say this is a half scale, this is a half scale, these two half scales are brought together, but the seat is deeper in the valve body, so the seat is basically not touched by the electrobeam. So the electrobeam goes in this area and the seats are located here and there. So the seats are not touched. The advantage is that I can now machine my seats in a plane. So I can machine the first half of the valve. So I can make my butter layer, I can put my stellite on straight direct on the valve body, because the integral seated is forged in that half scale, and then I melt these two half scales together. So I do have integral seated valves, and these materials of the seats are not damaged by the heat treatment afterwards either. So once the valve is electrobeam welded and heat treated, I just have to a final grinding of my seat surface and my valve is ready. My valve body is ready. Is that a little bit an answer, or is there any question?
That's perfect, Carol. I think that answers that one. Thank you. I'll give you another question. What are the differences and limitations in quickly warming up a cast valve versus a forged valve? For example, at what line size might you prefer one over the other? So differences in between casting and forging and size-wise, and warming them up very quickly.
Yes, well, let's say the old style valves we're using, and we have the regular recommended 2 or 3 degrees per minute. This can be applied on both a cast valve or a forged valve. But these requirements nowadays are not valid anymore. I want to ramp up much quicker. I want to have my HRSG as quick as possible on the grid. So my ramping figures are going up and up and up. Well, the forged material valves, and even if I have a valve made out of a block, which is basically a square piece with a round center, does have a very limited heating up radius, because the wall thicknesses all over the place are varying. If you have the forged valves, the hollow forged valves, they are already 2 steps better, because they are, I will not say maximum optimized, but they are much better in wall thickness, in equal wall thicknesses all over the place, all over the valve, so they will heat up much more regularly. So let's say these valves can do 6, 7, 8, 10 degrees C per minute, something like that. We can calculate this if you want. And then we have the fast moving valves, which are ramping up in 20 minutes from environmental temperatures up to 600 degrees C, so that is roughly the 30 degree a minute. These valves have to be special machined, and these valves have to be special constructed. The next valves, the near future, the next generation of these valves, they are teased by requirements of going up to 40 and 50 degrees per minute. And then these valves are not okay anymore, because the wall thickness is too thick due to the material, so then we have to go to a higher material. And then, if we translate that into electrobeam welding, the electrobeam welding at this very moment, although we are now in the test phase of getting these valves approved, getting these procedures approved, but these valves nowadays, of the future will be that these electrobeam welded valves can be forged to exactly the wall thickness you need, not more than that, and that these electrobeam welded valves are then the future, that they can stand these very high ramping figures. That is a little bit the history of valves. And if you then go back, if I have a main steam valve based on a casting, so or a WC9 or a C12A casting, the wall thickness of that valve is immense, is very thick. This valve is very heavy. But you can imagine that if I have casting defects in the valve body, that the heat transfer through that defect, if there is a crack, a thermal crack, or you have gas inclusions, or you have shrinkage holes, or whatever, that these defects are influencing the warming up of the valve body. Because they are blocking basically the equal heat transfer through the valve body. And if I do have a forging, I eliminate these casting failures and these shrinkage and temperature failures. So then at least I have homogeneous material which will heat up quicker. The next step is take a higher alloy, make the wall thickness thinner, and then the valve will heat up as quick as possible. But that is a whole development in the business, how that goes and goes and goes. I hope this is an overview, because it is an absolute hot item at this very moment in boiler making and in the new installations. And certainly this new 6,500 megawatt gas turbine generations by Siemens, by Ansaldo, by GE or by Mitsubishi, they are all aiming for these ramp-up figures to compensate the fluctuations in green energy, to fluctuate the uncertain production of windmills and the uncertain production of solar power. Then these installations have to ramp up as quick as possible to create a stable grid. So the demands on the green side of life is also a challenge for the old gas-fired systems. Any more questions, Martin?
There are a couple of other questions, Carol, but I'm afraid we're out of time. So is there any small wrap-up you want to do now?
Basically not. If you can do one or two questions more, I don't know when everybody has time or not.
Okay, one last question then. Does the buffer layer that you mentioned between the seat and the body introduce another potential failure point, or does it remove the failure point?
Both, of course. The butter layer, the flexible layer between the valve body or the valve retainer and the stellite hard-faced seat, if you do not have the butter layer, the chance that you have cracks or even completely damaged seats by thermal differentials is imminent. That will happen. So that seat without butter layer will damage and will cause emergency stops. On the other hand, if I do have the butter layer welded on, I do have an additional weld to make. So I have a potential that that weld will not have a good binding or whatever. If you do it properly, and believe me, guys like the PERSTA welding department is really of top quality, so they can really weld the butter layer, and then they can weld on that butter layer really good the stellite layers. So the chance that in this welding procedure something goes wrong is neglectable. The huge advantage is that you can be sure that the butter layer, the thick butter layer, is flexible enough to compensate the material expansion of the seat and the body material. And you can't imagine that it is millimeters, but when it's relatively small, the butter layer will absorb the differences between the seat and the back of the seat, and then you're sure that the seat construction of the valve is okay and will remain okay. I think that's the most fair answer I can give in this question.
Okay, no, that's fine, Carol. Thank you. And you've answered another question that's come in by default with that one. So if it's all right with you, I'll wrap up now.
Well, ladies and gentlemen, thanks for watching. Appreciated it very much. Hope to see you soon when we do other seminars, when we have more detailed seminars about production or welding or whatever. We're more than happy to invite you for these seminars, and Thanks for watching, highly appreciated. Have a nice time. Thank you.